Uh, so, hello all, welcome to this seventh lecture on the basics of Bharatiya Astronomy. As usual, we will start with prayers to our Gurus, Om Gurubhyo Namaha, and we will start with our Shanti Mantra. Asato ma sat gamaya, tamaso ma jyotir gamaya, mrityor ma amritam gamaya, Om Shanti Shanti Shanti. Okay,
Madhu, you're not sharing.
okay. Yeah, let me share screen. Let me share my entire screen. Okay. Can you see it now?
It's coming. Yes,
Okay.
but not
All
in presentation mode yet.
yes, yes, yes. I, okay. Okay.
Yeah, perfect.
Okay. Fine. Okay. So today's class is going to be a kind of a continuation of the last class, and where we will uh, logically complete the subject that we started with, which is the Bharatiya Astronomical Model. Uh, so we will do a quick recap of what we discussed in the class last week. Uh, we will, we will then talk a little bit more about the Indian Astronomical Model. Uh, this it's not necessarily going to be sequence, so we will revisit some parts that we discussed earlier, and then we'll introduce some new concepts, and then we'll also have some Q&A towards the end of it to logically close off this topic, right? Uh, okay, Bharatiya Astronomical Model. So we saw this last time. So let's begin this week also with let's say a teaser. Okay, can you identify what is being shown here? Any guess? I mean, I know it's very vague and abstract diagram, but can anyone take a shot at what this could be?
Is it a sundial?
No, it is not a sundial. But one clue I can give is it's a very, very ancient, famous monument. It's part of a very ancient, famous monument.
Huh.
I mean, if you make a guess, definitely the top three, one of the top three guesses will be correct. Okay. Anyway, let me reveal it. Okay, or let me give you one more clue before I reveal it. Okay. Now, uh, this one points to a particular star in the sky, right? Which is called as Thuban. Okay, so this part of the monument is aligned to this star. You know, the way it has been architected is such that this points to this star. Now, with this clue, uh, can you imagine what this could be? And one more clue: this is not in India.
Oh, is it the pyramids?
Perfect. Yes, it is indeed the the Giza pyramid. So, the Giza pyramid is built in a way that there are many chambers inside the pyramid called as air shafts, right? Now these different shafts are built in a way that they are aligned to different stars which indicate certain cardinal directions, right? So if you look at so this is the southern shaft. Towards the left it points to stars such as the Orion belt, which incidentally last week we saw a beautiful image that Ajay ji had presented. I think we also have the Sirius, which is one of the brightest stars. However, on the northern side, right, it points to this star called Thuban, right? Now, Thuban it's you can actually see it in the sky today, right? It's not a very prominent star. It's actually the alpha star of the constellation called Draco, but it is not a very prominent star, right? Uh, However, it has a reason why it is an alpha, right? The reason it is alpha was that it was the pole star of those times, right? So we are talking about timelines like 2700 BC for the pyramids, where the poles, although it was a very no, not a very bright star, it was an important star because it was the star that was closest to the celestial pole and hence was the pole star of those times. And the pyramids were built in such a way that certain air shafts, especially the northern air shaft of the uh, what is called as the king's chamber, was made to point to the Thuban star. Right now, why are we even having this discussion in this class? Can anyone take a guess? What is the significance of this to Indian astronomy and what we discussed last time? Okay, so now let's hypothetically say if the Giza pyramids were built today, and if we wanted to point to the star that is closest to the northern celestial pole, it is no longer Thuban. Why? Because due to the effect of the precession, the the pole star is now what we know as the Polaris or the northern pole stars today. So if the pyramids were to be built today, and there was an air chamber, air shaft to denote uh, the north pole, it would actually be pointing to Polaris. So what has happened is between 2700 BCE and today, the precession of the Earth or the wobble of the Earth has caused the northern celestial pole of the Earth to align with the pole star as opposed to the Thuban star that was during the times of pyramids. So I think this is one more, uh, let's say, another civilization, marking or another evidence from history which shows that the precession has uh, has actually happened. So that the North Pole Star has changed from Tuban to Polaris, and the Pole Star will keep changing, right? So the Pole Star, as the precession happens, it will keep changing to the different stars near the celestial pole, and incidentally, at some point of time, it will align with what is called as Vega. So Vega is the fifth brightest star in the night sky. It's very prominent in the northern uh, constellation of I don't know which constellation name. I think Lyra, but you could see that Vega is also the Abhijit, what we call as the Abhijit star, right? Which was the 28th star in our system. So at some point of time, Vega, the northern celestial pole, will align with Abhijit, and Abhijit will actually be the pole star during that era, right? So this again emphasizes the effect of precession, and precession was something that was also observed by other civilization in addition to our Indian civilization as well. So I just wanted to kind of introduce the topic. Now, before we get into things, we will quickly brush up certain concepts that we studied last week, right? I mean, of course, I know we didn't touch upon these directly, like like the slides that I'm showing today, but we did cover these concepts, right? So one of the
Mostly,
first.
we're
Okay.
seeing the notes.
Okay, got it. So let me.
Okay.
How about now? Is it
Still notes.
still notes? Okay. Now let me do
Yeah,
this.
that is
Now it's
good.
good.
No. Back.
Yeah.
For a minute, it was good. Yeah.
Okay. Okay. Fine. No problem. I'll proceed with this. Okay.
This
So
is
we
good.
saw. Yeah. So we saw the celestial sphere, right? Now, what is a celestial sphere? So it's the easiest way to understand what a celestial sphere is. You go and stand, in your terrace or in an open field today, and with you as the center, you just draw a globe or a sphere that stretches in all the directions, to the sky, right? Up to the sky, right? So you are at the center of a huge, massive, uh, universal globe, right? Now that is the celestial sphere. Now the celestial sphere has something called as the celestial equator, because of course it's a sphere, so it's got to have an equator, which is the largest bulge across the Earth, and then it also has the, if you draw a line and in the center of the Earth, the points where it extends to are the northern celestial pole and the southern celestial pole, right? And in this sphere, and basically you can place the stars at any point in the sphere, and uh, you can say that the position of the star is so and so, right? Now the units for measuring the positions of the stars in the celestial sphere are what we call as the right ascension and the declination, right? So this is similar to the latitude and the longitude that we use for Earth coordinates, right? So specifically, in the east-west direction, it is measured using the right, a unit called as the right ascension, right? And in the north-south direction, it is measured using what we call as the declination. Okay. So now, obviously, there's a 0 point for this coordinate system, and that is the vernal equinox, right? So the vernal equinox is the 0 point, and it is at zero. So the right ascension is measured in hour, minutes, and seconds. The declination is measured in degree, minute, and seconds, right? So, for example, if I'm talking about vernal equinox, it is at 0 hours, 0 minutes, and 0 seconds, right? Whereas if I'm talking about uh, the other equinox, which is the autumnal equinox, then it is exactly halfway around, which is 12 hours, 0 minutes, and 0 seconds. So I think it's a very simple concept, but but that's the idea of right ascension and declination and the celestial sphere. Right now, the celestial sphere. Okay, so yeah, I think this just captures whatever it is. It's similar to lat long on the surface, except that the vernal equinox is the origin, and you can uniquely designate any celestial object, and it is measured from 0 to 24 hours, as if it's like a 24-hour clock wrapped around the sky. And the declination is like the latitude, right? Because it goes north south. So just to give you an example, the Sirius, which is the brightest visible star in the sky today, has a right ascension of 6 hours and 45 minutes and a declination of 16 degrees and 43 minutes. So what does this mean? So it's located about 6 and 3/4 hours east of the vernal equinox and about 16.7 south of the celestial equator. Why south? Because it is a negative declination, right? So if I were to go and try to locate the Sirius star tonight, I don't know if we can locate it tonight, but if you have to, you should slightly look at approximately 16 degrees south of the celestial of where you are standing, right? Slightly go to the southern direction and go slightly east. So somewhere in the southeast direction, not too much, you'll actually be able to spot the brightest star, Sirius. So it's a quick introduction to the celestial sphere and the right ascension and declination units. Right now, this
Sirius
is
at this point of time is early morning.
sorry.
That
What was it?
you can actually see Sirius early morning. So that is that is where I got the Orion picture from last time.
Oh, perfect, perfect. Okay, yeah, yeah, that's correct. Yeah. Uh, okay. So Sirius, of course, is known as the dog star as well, and it's prominent in the sky in the summer during the summer evenings, right? Yeah. So we are close to winter, so it's somewhere in the mornings today. But yeah, it's an interesting star. Now, however, there is also something called the ecliptic, right? Now, the ecliptic is the direction, is the path in which the different planets, the sun the moon, and the other planets, they are all present in the path of the ecliptic. We also call this loosely as the zodiacal line, right, or the zodiacal band, right? Uh, so the ecliptic and the celestial sphere are, because the Earth is tilted, right? Because the Earth is tilted at 23.5 degree with respect to the, so the celestial equator and the ecliptic are tilted at an angle of 23.5 degrees to each other, which causes uh, you know, uh, the poles to actually get large amounts of sunlight during their summer times. Whereas if you move closer to the equator, the length of the days and the nights are pretty much equal almost all of the year. With a very very marginal differences. It's caused because of the tilt of the. So essentially, the ecliptic and the celestial equator or the celestial sphere are tilted at 23.5 degrees to each other, right? And the points where these are meeting, right, which is also the days in which the length of the day will be equal to the length of the night, is what we call as the vernal equinox and the autumnal equinox, right? Now, the days where either the daytime is too long compared to the night, or the nighttime is too long compared to the dark, or compared to the night, are the summer solstice and the winter solstices, respectively, right, in the northern hemisphere, right? So so the takeaway is that just remember that the ecliptic is the band where the motions of the planets happen, and uh, what we call as the nakshatras are also aligned along this ecliptic. Rather, they provide a fixed point of reference uh, in the background of the dynamic planets that are moving. Right. So that is the ecliptic, right? And then because of this, like we just talked about, we have equinoxes and solstices, right? So where the ecliptic crosses the equatorial plane, they are called equinoxes. And like we said, 12 hours of daylight and 12 hours of night. Um, and the vernal point. So the vernal point has an array of 0, 0, 0 and a longitude of 0 as well. So because it's the 0 point coordinate, and the autumnal point also has the array as 12, 0, 0 and a longitude of 180, and the extremes of the northern extreme of the sun is the summer solstice. The southern extreme of the sun is the winter solstice, typically happening around December 22nd. And yeah, now the last one is important, right? Both the equinoxes and the solstice are in motion relative to the fixed stars due to precession. Now, if there were no precession, right, the vernal equinox and the autumnal equinox and the solstice and winter solstice, everything would be happening at the same point in space year on year. But because the Earth precesses, these points the positions of these points are changing on a year on year basis in relation to the fixed background of stars. So we touched upon some of these concepts in the in the previous class as well, right? So yeah, so just refreshing some basic ideas of the spherical coordinates and the concept of equinoxes and solstices. We also saw that our ancient Indians, especially belonging to the Vedanga Jyotisha era, were very much interested in understanding or pinning down where this vernal equinox point is to a very accurate manner, right? And we also saw some of the reasons for that. Okay, sorry, one second. I'm just trying to go back to an earlier slide. Okay, so we also saw that they were very much interested in understanding the position of the vernal equinox for the following reasons, right? Festivals, predicting seasons, astronomical tables, eclipses, preparing the panchanga, everything was based on the accurate determination of the position of the vernal equinox. And hence, they used instruments such as the gnomon, which is kind of part of the overall sundial instrument. And then they, on top of the observations, they applied calculations, and they were able to not only accurately pin down the vernal equinox point, but in that process, they also observed that the position of the vernal equinox was changing on a year on year basis. And in order to reconcile this, they came up with the what is called as the precession of the equinoxes, right? So we also saw how Varahamihira was in during his time stating where the Uttarayana and the Dakshinayana points were present, right? So he says that it is at the beginning of Cancer, which is aligned with Punarvasu, the second pada, I think, or fourth pada, fourth pada of Punarvasu, and from the initial and the summer solstice was happening at the initial point of sign of Capricorn, which is Uttarashada, second pada, right? And he also notes that during the time of Vedanga Jyotisha, it was respectively at Aslesha and Dhanishta. So Varahemihira had already observed that these points have moved between the Vedanga Jyotisha time and during his time, and he had uh, understood the concept of precession, and he, like many Indian astronomical, many Indian astronomers, had also tried to calculate what is the difference in the vernal equinox point, or what is the rate of the change of the vernal equinox point on a year on year basis. And they were able to arrive at this value called as the 54 arc seconds per year, right? So there was every year, the vernal equinox point was shifting at a rate of 54 arc seconds, uh, towards the west, right? So it was continuously moving against the fixed background of stars. Right? So we saw some of these concepts last time as well, right? We also touched briefly upon the 27 nakshatras, starting from Ashwini, Bharani, Kritika, Rohini. Like I said, it represents the fixed background of stars against which the dynamic motion of the planets happens in the foreground. Nakshatra system is very unique to Bharatiya astronomy. And we also saw a little bit about the segmentation of the 360 degrees of the night sky. So each nakshatra, so the night, if you think that the night sky is 360 degrees, then which it is, then every nakshatra occupies what is 800 arc minutes, which is a simple division of 360 by 27. And each nakshatra is further subdivided into four parts, right? So there are 108 padas in total across the 360 degrees and across the 12 rashis that are there, right? And so, so this is a slightly more of, like a fine-grained version of the nakshatra padas. So uh, if you look at it, so you can see that uh, every nakshatra has four padas, as we saw, right? And every rasi has nine uh, padas in it. So what that means is the first rasi. So if you take the first rasi, it has four padas of Ashwini, it has 4 padas of Bharani, and it has 1 pada of Kritika. Right now, so here the Rasi boundary ends, but the Nakshatra boundary is not here. The Nakshatra boundary is spanning across two Rashis, one of which is Aries and the next one which is Taurus, right? Or Mesha and Rishabha respectively. So you have 1 pada of Kritika present in Mesha and 3 padas of Kritika present in Rishabha, right? Now, and then the Rohini, because it has 4 padas, will fully fit into Rishabha. Now, after 3 plus 4, 7 padas have been taken. So you have 2 padas left for the next star, which is Mrigashirisha. Now, the next 2 padas of Mrigashirisha have to be fitted into the next uh, Rashi, which is Mithuna, and so on and so forth, right? So, like that, all the 27 nakshatras with their 108 padas are distributed in the 360 degrees of the night sky, right? So, important takeaway here is that the nakshatra boundaries and the Rasi boundaries are different, and the nakshatras cross the Rashi boundaries, right? So, in different ways. So, for example, uh, nakshatras that belong to completely one full Rasi are the following ones. So, if you look at Ashwini, Bharani, they are completely within Mesha. If you look at Rohini, it is completely within Rishabha. If you look at Ardra, it is completely inside this Mithuna. Similarly, if you look at Pushya and Aslesha, it is completely within Kataka, and so on and so forth, right? However, and most of the nakshatras are like this, right? However, there are some nakshatras which have 1 pada in the first Rasi and 3 padas in the second Rasi, right? So, example is Kritika. Kritika has 1 pada in Mesha and it has 3 padas in Rishabha. Similarly, if you take Uttara Falguni here, it has 1 pada in Simha and it has 3 padas in Kanya. Similarly, Uttara Shada has 1 pada in Dhanush and 3 padas in Makara. Right? And there are some which have two, right? So Mrigashirisha, Chitra, and Dhanishta. So if you look at Mrigashirisha, it has 2 padas in Mithuna, in Rishabha, and 2 padas in Mithuna. Similarly, Chitra has 2 padas in Kanya and 2 in Tula, and similarly Dhanishta. And then lastly, there are nakshatras where there are 3 padas in the first Rasi and 1 pada in the second Rasi. Typical example is Punarvasu. Punarvasu has 3 padas in Mithuna and 1 in Kataka. Vishaka has 3 in Tula and 1 in Vrishchika, and so on and so forth. Right. So I just wanted you to understand that it is, it's so we are trying to fit an odd number of nakshatras into a kind of an even numbered system, and hence uh, there is not exact alignment of the Rasi and Nakshatra. Of course, this does not have any astronomical significance per se. It is more for astrology reasons. But again, our ancestors did not really distinguish a lot between astronomy and astrology. And I just wanted to uh, cover this as part of covering the nakshatra system as well. Right. So this is about the nakshatras. And then we talked about we talked about how nakshatras have been referenced in texts in different ways. So in the Rig Veda, it is talked about in a very poetic form. In the Vedanga Jyotisha, it was more aligned to the needs of the sacrifice, right? So we saw that whenever a person is supposed to conduct the yajna, he is supposed to uh, say the name of the nakshatra in which he was born. And sometimes, if he did not know, the first syllables of his name were taken and mapped to the corresponding nakshatra, and that nakshatra was used as his nakshatra for the purposes of the yajna. Right. So this is an example of how the yajna was determining everything during the Vedanga Jyotisha times. And then the more the last 14th, 15th century time frames, people are trying to, or astronomers are trying to mathematically model the nakshatra positions, right? And the positions of the moon as it traverses through the nakshatra, and sharpening or refining their calculations to for various purposes, right? Which is the basis of the panchangas also that we see today. So we are able to very accurately say that certain uh, grahas are moving into certain positions of the sky because of the very meticulous mathematical modeling that has happened in the more recent times in Indian astronomy. We saw that as well last week. And of course, we touched upon the precession of the equinoxes. We talked about it quite enough number of times now. We also saw that the precession happens because of the cumulative effect of the gravitational forces of the sun and the moon. And the precession cycle is approximately 26,000 years. And uh, the precession, uh, uh, so the precession causes the equinox point to shift against the backdrop of stars. It also causes the pole star or the celestial pole to change position as time goes by, right? Although it is happening at a rate of approximately 54 arc seconds per year. We don't notice that obviously in the time scales that we live, but over a larger period of time, it uh, makes a significant difference, right? Now, let me, I just wanted to quickly illustrate that point as well, right? So let's take Makara Sankaranti, for example, right? Now, what is Makara Sankaranti, right? Makara Sankaranti is sun moving from the uh, Dhanur Rashi into the Makara Rashi, right? So that is the Makara Sankaranti. It is the transition of sun into Makara Rashi, right? By the way, you are able to see my screen, right, where Jagannath Hora is displayed. Uh,
Yes.
okay.
Yeah.
Now,
Yeah.
now let's look at Makara Sankaranti for the year of 2025, right? So approximately Jan 14th, 2025, right? Yeah. So you see that the sun has already entered Makara. So this is Dhanush and this is Makara. If I just go a day back, sun is here. So sometime during between Jan 13th to Jan 14th, sun has entered Makara. This is as of today, Jan 14, 2025. However, so in South, of course, we celebrate as Pongal. It's celebrated as Makara Sankaranti, and of course, in different parts of India, it is celebrated as different festivals because the sun moving into Makara is a somehow it has been a very significant event for all our ancient people, right? Uh, However, if I go back in time, so let me go back to an arbitrary time, right? 1745, and say Jan 14th, right? So here you see that the sun has already moved into Makara here, right? But it has actually moved 4 degrees. So remember, in 2025 we saw it was only 0 degrees, but here it has actually moved 4 degrees. So let's rewind a bit, okay? Jan 4. So keep track of this. Jan 14th. This is Jan 13th. Still, sun is in Makara. Jan 12th, sun is in Makara. Jan 11th, sun is still in Makara. Now, Jan 10th, sun is still in Makara. Right. Now, Jan 9th, sun was in Dhanush. So, if I now play it back, then between Jan 9th and Jan 10th is when sun is transiting from Dhanush and Makara. So, what does this mean? The Makara Sankranti during 1745 was actually happening on between Jan 9th and 10th. So maybe Jan 10th, they were celebrating Pongal, right, in Tamil Nadu and Makara Sankranti all over the world, right? So also all over India. Now, why does this happen? Again, this is another way of looking at how the precession has because all this Makara, Danush, what these are all the background static fixed background backdrop of stars, and we are seeing where sun is moving from one point to another in that background backdrop of stars, right? And sun has and this keeps changing because of the precession, and because of that the position at which this transition happens is changing year by year. And in 1745 it was happening around Jan 10th. So this date of this date called Pongal, which we celebrate in Tamil Nadu as Jan 14th today, will keep changing. So typically, uh, every 72 years, the date will actually advance by one. So 72 years from now, we will be celebrating Pongal more and more in Jan 15th, 16th, and 17th. It will just keep going like that, right? So this is uh, another let's say an example or an illustration of the precision. Yes, Ajay, you have a question?
Yeah, I think it might be useful for the audience to understand that because January 14th, the Makar Sankranti has been traditionally associated with Uttarayana. So, and now from most the astronomical models, we know that winter solstice is 21st, 22nd December or so. So, I think it will be useful to know that at what time was the winter solstice and Makar Sankranti actually merged together.
Yeah, it's a very interesting problem, Ajay. Maybe we could take it as an assignment, right? Although it's
Yes.
a little bit mathematically not very trivial, we could take it as an assignment and align our winter solstice with the Uttarayana and see when that time frame was, right? Yeah, I think that will be an interesting one. Thank you, Ajay, for that. But see, thanks for that. It also kind of leads into our next discussion, right? Which is okay. Oops, sorry, I don't want to see. We have seen this before. I'll not go into it again, right? So the Bharatiya Astronomical Model had a need for two coordinate systems for different purposes, right? Indian astronomers developed two distinct coordinate systems for measuring, one for measuring celestial phenomena, which is the skybound space-centric measurements. At the same time, for matters that were more terrestrial in nature, right? Uh, they were they needed an earthbound calendar as well. So they had a need for two different systems, right? And they called it as Nirayana, right? So the skybound space-centric measurements is called as the sidereal system or the Nirayana. It of course comes from the Sanskrit root, which is Nir Ayana, which is without relation to the Ayana, right? So sidereal, by the way, the word sidereal means related to the stars. So you can already guess that the Nirayana is with respect to the fixed background of the stars. So that is the frame of reference for the Nirayana system, right? So uh, see the equinoxes, as we say, keeps shifting every every time because of the precession. However, this system does not care about the equinoxes, right? It is only linked to the fixed stars or the nakshatra background or the background of the nakshatras, right? Now, why did we need this? Okay, so before we say why did we need this, the other system is called as the tropical system. So obviously, tropical means it's more earth way, local, right? It's called as Sayana, right? So Sa plus Ayana, Sayana. It says with the Ayana. That is here the reference point is the equinox. So you see here the reference point is the fixed star, which is static. Here the reference point is the equinox, which is not static because of precession, right? So a system that is based on the fixed stars is called as the Nirayana, whereas a system that is based on the dynamic equinoxes is called as the Sayana, right? So they needed these two calendrical systems for different reasons, right? So, for example, the sky-bound space-centric measure, where if for questions like when did Jupiter enter Kataka, right? Because I want to perform the marriage of my daughter when Jupiter enters Kataka, right? So so in order to answer such questions, I will use the Nirayana system, right? Or questions that were related to synchronizing of the lunar and the solar calendars. Does this year have an Adhika? So which means what? So what? The sun and the moon, where are they conjoining or coming into the same place against a fixed backdrop of stars? That is when the Adhika Masa happens. So that such questions are answered by the sidereal system, right? Or when does sun enter Makara, which we just saw, right? Or I want to track positions of Rahu Ketu, right? Or the dates of Grahanas, right? So for such matters, they used the Nirayana system, right? And interestingly, today in all our panchangas and all our the astrological software and astrological for all astrological purposes, we use the Nirayana because we want to track the movement of these planets against the backdrop of the stars, right? Now, then what is the use of this Sayana? So Sayana answers questions like when is my season starting? When is my summer season starting? Because I have to, sow some seeds, right? Or when is my springtime starting? Right? Which is because I'll have to celebrate Holi during that time, right? Or has the new year begun? Because in the beginning of the new year, I want to celebrate, or sorry, I want to plan for the rituals. So the cycle of rituals happened at the beginning of the year and ended at the end of the year, right? So when should I start my ritual cycle, right? So for such earthly matters, when should I sow my crops? When should I harvest my crops? When are my festivals coming? All those questions were for those questions they were using the Sayana system, right? So this is an important one, and just wanted to we just need to understand this, right? Now, again, it's the same thing. I'm just saying in a different way. The Nirayana system or the sidereal system. It's important to understand that we needed a reference point, and that reference point is set as the beginning of the Mesha, right? It's also called as the Meshadi, Me, Meshasya Adi, Meshadi, and then it is a fixed point in the background of stars. And then in this system, the new year is supposed to start when the sun is present in the uh, Mesha, in the beginning of Mesha, right? So if you look at your Tamil New Year, today, it is typically celebrated on April 14th nowadays, right? And that is the time when Sun transits from the last pada of Meena to the first pada of Mesha, right? Which will always be on April 14th. Of course, again with the precision that will also keep changing over the years, right? But today it is celebrated as April 14th. Whereas in the case of tropical system, the reference point is the vernal equinox, right? Now the vernal equinox, because of precision, keeps moving, and the new year is calculated from equinox to equinox, not from sun in the backdrop of Mesha this year to sun in the backdrop of Mesha next year. Whereas it is from this year's vernal equinox to next year's vernal equinox. Now, because of the precession, this equinox point is shifting, right? And it is shifting in the opposite direction, which means that the tropical year, because I'm measuring it from equinox to equinox, it is shrinking every year, right? Whereas the sidereal year, because it is always against a fixed backdrop, it is a fixed number. So the sidereal year is, yeah, Okay. So we were talking about so how the sidereal year. Okay, let me share my screen again.
Just a time check. It's 10 minutes
Yes.
left. Yeah.
No, I think we are almost done. We are almost
Yeah.
done.
Okay. No problem.
Yeah. Um, yeah. So okay. So the sidereal year is always greater than the tropical year by this 20 minutes and 24.5 seconds, right? Now, obviously, this difference is because we are using two different Ayana systems, Nirayana and Sayana, right? Uh, and the difference between these two systems is called as the Ayanamsa, right? Uh, like I said earlier, Bharatiya Astronomy always used Nirayana longitude for most purposes, right? Longitude measured from a fixed star, right? Now the difference between these two is an indicator of the extent of precession, right? Which is called as Ayanamsa, right? So the Sayana longitude minus the Nirayana longitude always is the Ayanamsa. So for example, during 285 common era, the vernal equinox was at the beginning of Ashwini Nakshatra, exactly, right? So at the time, the Sayana, see, because the Sayana longitude was the same as the Nirayana longitude, right? The Ayanamsa was zero during that time, right? However, at present, because of this 54 minute, or sorry, 54 arc second change in every year, the position of the vernal equinox is somewhere. Sorry about that.
Yeah. True.
I hope it doesn't happen one more time. Okay. Yeah. Okay. Okay. So I don't know till what time I talk, but at present the position of the vernal equinox is 24 degrees. So I think we saw this in the last class, right, where uh, we took the example of the Ugadi, right, and we showed that the Ugadi was happening not at the beginning of Mesha, but it was actually happening 24 degrees to the west of the beginning of Mesha, somewhere in the Uttara Bhadrapada nakshatras, right? But important point to remember is that the Narayana system is the one that is used by our Panchangas, and that is the one that is used by the astrology community as well, right? Now, so this precision value, like I said, our Indian astronomers were aware of precision. They needed to understand what the precision values to pin the vernal equinox. So they were actively observing and calculating the precision, and different values were uh, hypothesized by different astronomers. There are some Chinese astronomers also here. There are some, I think, Greek astronomers, Vruddha Aryabhatta, everyone is there, but mostly they uh, they're all centered around this 54 arc minutes per year, right? Somewhere here. So it's kind of centered around here, and you can clearly see that most of our Indian astronomers are lying in that 54 degrees plus or minus, right? So which means Indian astronomers had a very accurate model. And by the way, it is accepted today by modern science and through modern astronomical instrumentation and all that, as the precision is around 54 arc minutes per arc seconds. Sorry, this should not be arc minutes. It should be arc seconds per year. And our astronomers were actually very close to that value, right? And it was also the astronomers were actually improvising, compared to the previous values. They were not accepting it, they were challenging it, they were improving it, and they were refining the calculations to arrive at a more accurate value, right? So there was also, see, this precision also, there's a variation of this precision called as the trepidation model, where see, it's not like a smooth wobble that happens. Rather, the wobble happens kind of back and forth, right? So that's like the top is kind of shaking, as it comes to a stop, right? Along with the wobbling. So that shaking, like additional shaking effect, is the trepitation model. However, we don't want to go into those details. And then, yeah, some of these values probably, the ones that Indian astronomers calculated, maybe they were, communicated to the other civilizations like the Arab civilization or to the Greek civilizations. So those possibilities were also there. But I think it's important to understand that not only were we aware of this phenomenon, but we were also observing it. We were also accurately calculating it, and I think it really represents a very high degree of scientific thought, that existed during that time, right? So I think with that, maybe we can um, close this topic for today. And I think, see, like I said, the astronomical model has different parts, right? One is the spherical geometry and the precession and all that, which we discussed in the last two classes. Then there is this concept of time, which we will touch upon, at a later part of the course. But for now, I just wanted to, cover this important aspect. So yeah, I think that kind of covers this topic. So any questions, any suggestions, comments that you may have, you can please ask them now. Yeah. Ram, any questions?
Yeah, so I think one of it, I just asked on the thing, Ajay quickly responded. So after, sometimes ignorance is bliss, so we don't question some of the things. Now that, so I was just
Mhm.
asking, which one is the moon's orbit aligned to, right? So that I think Inga answered. So the
Yeah.
other question I had is, it's more related to when we look at the Jyotisham, right? Where some of the calculations that we were taught uses what is called the Rashi Mana, the amount of kind of, so to say, it's a measure of kind of approximately proportional to the measure of the day, right? Because
Mhm.
we are using
Mhm.
Suryodhayam as the point of reference due to the
Mhm.
I mean, like before we had precise clocks where you could clock the midnight, right? And
Yeah.
that seems to be pretty aligned to, so the values looks pretty much symmetrical with reference to equinox.
Mhm. Okay. Mhm.
And uh, today it's aligned with Mesha,
Mhm. Okay.
right? And so you said so currently April 14th happens with
Mm.
sun entering Mesha, right?
Correct.
So that would have probably then moved along as how the new year um, for the new year alignment with this transition happened,
Mhm.
right? So now the
Yeah.
last, that would then mean that it will break that symmetry of equinox
Mm.
versus how we
Mm.
actually calculate the Rashimana symmetry starting from Mesha all the way to uh,
Mm. Correct.
Meenam, right?
Correct. Yeah, that's correct. So I think, so. We are referring to how the sun, how, because the longer days are also
Mm-hmm.
shifting. See, the length of the
Yes.
day
Hmm.
is also shifting over the years, right? See, today, June 21st is the longest day, right? However,
Yes.
if you rewind a few centuries back, the longest day would
Mm-hmm.
not be June 21 because the solstice itself is moving, right? Because
Hmm.
so now the Rashimana system that you are saying, based on which the astrological calculations are made, will also change based on that, right? So, uh, so see, today astrological calculations are based on what we call as the ephemeris, right? So in the ephemeris, you have the daily positions, very accurate positions of every planet, and So you have it for every day, like Jan 1, Jan 2, Jan 3, all the way till December 31st, right? Now,
Uh-huh. Uh-huh.
if you look at so that ephemeris would have been very different many centuries back, right? Where uh, the time that sun is actually spending transiting, say, for example, a Rishabha Rasi would have been actually more compared to it Kataka being today,
Actually,
right?
you are right. Now that you are explaining that, I had a panchang next to me. I was
Mm,
just looking at it. The total Rashomana for Mesha is 430, but for the last month, it
mm,
actually is not 430. Goes down to 407, which explains the drift in
mm,
from the vernal equinox to
mm.
the 24 degrees that you mentioned. So because
Yeah,
otherwise it would have been 430 for both Mesha
yeah,
and
yeah, yeah,
Meena, right?
yeah, yeah.
Okay.
See, of course, see, I'm not very familiar with this Rashimana term. I've not worked with it, but see, I think the bottom line is these so-called Rashis and Nakshatras. They're all, you see, everything is non-linear in the actual world, right? We are trying to
Yes. Yeah.
break. So, see, we are trying to put it or compartmentalize into 12 Rasis, 27 Nakshatras, right? But in real life, because of the tilt of the earth, the sun actually spends. So if you look at it right, the Kataka is actually more than 30 degrees in length because of this, which is
Yes.
which if you project into time gives a longer time spent by sun in a Kataka Rasi compared to a Makara Rasi, right? So it is happening because of the
Yes.
non-linearity of the system, which is also caused by the tilt. It's caused by different factors, right?
Mm,
It's caused by the tilt of the earth. It is caused by the precession of the equinoxes, and it is
mm.
caused, so all of these are combining, and it is not static. It's all changing every year in different ways, right? So I think,
Yes. Yes.
but the
Yeah.
good thing was, I think although it was changing, our astronomers have found a way to measure this change and document them in these very what do you call detailed panchangas, which we call as ephemeris today. And today we just need to look at the ephemeris. See, like you have the Rashimana, you have certain numbers, right? Now all those numbers
Yes. Yeah.
which you directly take and apply to calculate the lagna in a horoscope, they are all being worked
Mm.
out in the background based on the different factors that affect it, which includes the precision, which includes the changing of the equinoxes and everything, the motion of the earth and everything is included. Yeah, so I think we just
That's
it's a
actually right.
dynamic.
Now that you explain that, it's actually kind of starting to get clear. So because for us, rest of the real Panchamabhuta planets, that becomes very simple and straightforward, right? Because that is just simply observed and documented. It's
Yeah.
only where the confusion where it starts is only when you between sun and where you mark the ascendancy or the lagna, right?
Mm,
That is where the mainly the whole precision needs to be factored in, right? So
yes.
that's where the whole the calculations and the
Mm,
adjustments needs to be factored in. Even
yeah, yeah.
moon kind of is okay because we already have a reference of moon with reference to the nakshatras, right? So that is how we do that. So that means
Correct.
moon, Rahu, Ketu will fall in place. The rest of the planets will fall in place. The only thing that needs to be adjusted in how we calculate a horoscope would be is based on the precession versus the sun, which will basically decide where the ascendancy will fall. Right?
Yeah, yeah,
Okay. I
yeah.
think
I mean,
that
of
seems
course,
to
it.
actually make
I,
sense now.
I
Yeah.
yeah. I think. See, it impacts all the non-linearity impacts all the planets. It impacts the
Hmm.
faster moving planets more than the slower moving planets, right? So your sun,
True.
moon,
Yes. Yeah.
Mercury, Venus, Mars, Jupiter, Saturn, in that order will be,
Hmm.
so yeah, you will see that. So wherever you are using these for calculations, obviously you will see that impact. Yeah, more so for maybe sun and moon than anything else is what I would say. Yeah, yeah,
That's true. That's true.
yeah. Cool, cool.
Nice.
Uh,
Thanks,
yeah,
Gaurav. This was
thank you.
actually precision was one of the topics that had quite a bit of confusion before. So this was actually a good session. Thanks for it,
Thank you. Thank you
for
very
this
much. Thanks
detailed
for
session on this one.
yeah, thanks for patiently listening. And I really apologize for the technical glitches that happened in the middle. They were kind of beyond my control. Hopefully, it doesn't happen in the future. Yeah.
Yeah,
Um,
that's
Ajay,
all.
you want to talk a little bit about what's coming in the next few weeks?
Yeah, so basically the idea was that I was going to go through some of the astronomical sections of Srimad Bhagavatam over the next lecture, next maybe two lectures, and then also going to talk about the different contributions of the astronomers and so on. Um, However, one thing I wanted to confirm, just I suppose for the two of you at the moment, whether next week is going to be okay because of the Diwali and the associated events and all that. Is the next week and the week after, is that going to be okay for the two of you, or?
Actually, you know that you bring up, probably next week could be